So here's something that you wouldn't really have encountered too much in geometry, despite having dealt with angles there. And that's the idea that there's more than one way to produce what appears to be the same angle. That is to say, when we think of angles, we tend to think of them in terms of what they look like. If I asked you to draw an angle, you might draw something like this. Now, if you were really thinking about it, you might include an arc in the middle to show me what part of it we're talking about. Because there's another way we could do it. What if we went in this direction? Actually, for that matter, we don't even have these labeled as initial or terminal side. So we don't know if we're rotating from here up to there, or from there down to here. We don't know if we're rotating from here around, or from here around. There are actually multiple different ways to create an angle that has these two rays extending in those two positions. And that's what coterminal angles is about. The idea that there are multiple ways to produce an initial side and a terminal side in the same locations. Actually, because standard position of an angle always has the initial side in the same place, that's all automatic. The initial side will always be in the same place. So really what we're looking at is a matter of whether the terminal side also ends up in the same place in one angle as it does in another. So what I've done here is I've drawn three sets of initial and terminal sides. And all the initial sides, of course, are in the same place, as they always will be. But all of the terminal sides are in the same place. Now, what I did not include was the rotation. And that's actually very relevant. So the most basic way to do this would be to rotate in the positive direction directly to that terminal side. And we know that to be 90 degrees. Or in radian measure, we call it pi over 2 radians. But we can rotate in other ways and have our terminal side end up in the same place. Suppose we start with our initial side here, and we rotate in the clockwise, the negative direction. Well, certainly the amount of rotation is significantly more than it was there. However, we can still count. It's just in the other direction, 90 degrees, another 90 to 180, another 90 to 270. Oh, excuse me. Forgot the very important thing there, the negative sign. Now, I'm going to come back here and subscript this. I'm going to call this theta sub 0. I'll call this theta sub 1. Negative 270 degrees, or as we will know it in radians, negative 3 pi over 2 radians. 1 pi over 2, 2 pi over 2, 3 pi over 2. Now here's where it really gets wacky. Nowhere in geometry would you ever have seen negative angle measure, which again doesn't mean less than 0, it just means the opposite direction. But here's another thing you wouldn't have seen in geometry. Although any of you guys who are familiar with skateboarding or snowboarding should be familiar with this, it's the idea that you could have angles that are more than 360 degrees by going around more than once. What if we start here and we rotate in the positive direction, but we go right past where that terminal side is, all the way around, and keep going and then stop. And for that matter, we could continue around as many times as we wanted. Point being that this, while still being in the positive direction of positive rotation, this is considerably more rotation than that is. It's even more than this one was, because this one didn't even go a full circle in the opposite direction. This one goes all the way around and then some. So if we counted that, that would be 360 degrees plus another 90. That makes this 450 degrees. Or, in radians, it would be pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. An interesting thing, to be sure. We can have angles that are positive or negative. We can have angles that exceed a full rotation of the circle in either direction. In fact, when you think about it, there are infinitely many ways that we can create a terminal side that lies along the positive y-axis like that. We can go around twice, 3 times, 4 times, 5 times, 6 times. Or in the other direction once, or twice, or 3 times, or 4 times, or as many times as you can possibly imagine. Now, would we? No, it's possible, but typically we won't that often, but it does come up. So we have what's called the coterminal angle formula. And it's this idea that we have a base angle to start with, an initial angle. We call it theta sub 0. So if theta sub 0 is some initial angle, some base angle that we're working on, we're going to let theta sub n be equal to, well, it's going to have the amount of rotation of the original. That puts us in the position that we want to be in. And then from there, we can add as many turns of the circle as we want, because each additional turn will keep us landing back in the exact same spot. Where n is any integer, n then represents the number of full rotations of the circle. That's what the times 360 degrees is. This is one full turn, this many times. Now, if we were to do it in radians, it would be theta sub n is equal to theta sub 0 plus n times, instead of 360 degrees, 2 pi radians represents a full turn of the circle. Now, let's give these formulas a shot. Now again, we're going to be working primarily with radians, so I'm going to try and stick to that to kind of force us to get used to them here. Let's take a look at actually these angles in particular, and we'll start with this one because this one is perhaps the most obvious of it. For one thing, it is positive rotation. And for another thing, it's very easy to see how we can break this down into the original 90-degree angle and then an additional full turn. So let's say theta sub 0, our initial angle, is pi over 2 radians. And what we're going to do here is we're going to take that initial pi over 2 and we're going to add a full rotation of the circle. So I'm going to call that theta sub 1, which unfortunately gives us a slight contradiction there. We're going to come back and re-subscript that in a moment. This would be the original pi over 2 plus 1 full rotation of the circle beyond that. Now, all we need to do here is actually do the addition. And don't let the pi bother you. Think of it almost like a variable. If you're adding two things, you can just add the coefficient. So really what we need to do is we need to add the 1/2 and the 2. So here's a way to do that. To add fractions, we need a common denominator. So it would help if we perhaps wrote 2 pi as being over 1. And then to get a common denominator, we just do that. So we have pi over 2 plus 4 pi over 2, and that equals 5 pi over 2. Exactly what we had by counting the subdivisions. So the formula worked. Okay. Now this one's a little bit weird because it requires a change of direction. The formula is based on the idea that we always are going to start out by going to the angle in the original amount and direction. And then from there, we do our full rotations. So in this case, we have to think of it as if we went to the pi over 2 and then did a single negative rotation. So I'm now going to subscript this with -1, since we now have this concept of rotation, numbers of full rotations to go off of. And we're going to say that theta sub -1 is equal to the original pi over 2 plus -1 times 2 pi. One full rotation in the negative direction. So I'm going to leave that as addition and keep the negative attached to the 2 pi here. And just like over here, in order to add those, we're going to need a common denominator. And what we have now is 1 pi plus -4 pi, or 1 plus -4 is -3 pi over 2, which is what we had by counting subdivisions. Now, the formulas might seem a little unnecessary here because we started out with angles that were already drawn with rotations already drawn in. So we were able to get around it by counting subdivisions. There are some situations where that may not be the case. Perhaps, as often happens with these, what if I gave you the initial angle and didn't give you these and just said, find 2 coterminal angles? Then we wouldn't have an angle drawn to count subdivisions. We'd kind of have to use the formulas. I suppose what we could do is like this. We could place the terminal side and then just figure out a new rotation, but this point, you know me, I'm going to make you use the formula at some point. So, coterminal angles. Every angle has an infinite number of other angles that are coterminal to it, meaning they have the terminal side in the exact same positions, but the rotations used to get there are different. And it always differs by some number of full rotations of the circle. Coterminal angles will become relevant to certain things that come up later on. For now, it's something to help practice with radian measurement and getting used to different angles in radian measurement. And before the end of the semester, we will see places where the coterminal angles do actually become relevant.